Hi students. Now students, in this lecture we would be doing the writing down the equation of semi-batch reactor in terms of conversion X, right? And we know conversion concept that we have done earlier, right? So in the previous lecture we have done the equation of semi-batch reactor in terms of concentration, right? Now we would be writing down the equation in terms of conversion X, right? Now for any reaction A plus B giving you C plus D, right? This is how it would look like. Right here you have taken, say A, Na0 you have taken initially, right? This is a semi-batch reactor that already contains A, and to this semi-batch reactor, to carry out this reaction, you are adding reactant B, right? You are adding moles of reactant B into semi-batch reactor, right? This is how reaction is taking place. Now conversion, let's say for X, let's say for A is reacting with B to give you C and D, right? If you want to find conversion, that means how much of A has reacted, it would be number of moles of A reacted. Conversion is the ratio of number of moles of A reacted divided by number of moles of A initially taken, right? It would be Na is equals to, or it would be Na0 X. These are number of moles reacted, right? So how much number of moles would be remaining? Na0 minus number of moles reacted, right? Initially you have taken Na0, this much have reacted, right? In terms of conversion we have calculated. Conversion is conversion of reactants into products. Here conversion of A into products, right? So it would be Na0 1 minus X, right? This is your number of moles of A remaining, right? Initially taken minus reacted. Number of moles remaining, right, at any time t, right? It would be Na. So Na would be equal to Na0 Na0 1 minus X, right? Now similarly we will find how much of B is remaining at any time t, right? So number, let's write it over here, number of moles of B, right, at any time t, right? Now since you are adding B, let's say the molar flow rate would be FB0. Since it's flowing, so we always take molar flow rate, right? This molar flow rate is the number of moles flowing into the reactor, right? Now suppose initially you have taken NBI, number of moles of B in the reactor initially, let's say NBI, plus number of moles that you are adding into the reactor, right? It would be given by molar flow rate. At any time t, it would be given by integration 0 to FP0 dt, right? This much number of moles of B remaining at any time t, right? This is initially you have taken, right? Initially NBI is present in the reactor. Now at any time t you have added this much, right? Minus remaining, right? Minus would be initially you have taken. How much of B you have taken initially? Now we will write it in terms of A. If you remember, if we take it from this equation. We have done this earlier, right? How to write down the concentration of other reactants in terms of one of the reactants A. So here we will write it as Na0 X, right? This is your NB. NB is, sorry, moles of B reacted, right? The conversion is moles of B reacted upon moles of A initially taken. It would be NB initially, NB0, say it would be Na0X, right? So this is B remaining at any time T in terms of A, right? This is what we are writing. So this would be NB. Initially in the semi-batch reactor there is no B, right? So the B is 0 plus FB0. If you integrate this, it would come out to be NB0T minus Na0X, right? Now we know NB and Na, right, at any time T in this reactor in terms of conversion. Now we will do mole balance for A, right, for A, which is already there in the reactor. So it would be in minus out plus generation is equals to accumulation. This is the mole balance equation. In and out, since B is there in the reactor, right, it's not moving in, it's not moving out, so both these would be 0. Generation would be RA V is equals to, accumulation would be dNA upon dt, right? Now dNA upon dt can be calculated from here. dNA upon dt would be minus Na0 dx upon dt, right? Now we have got dNA upon dt in terms of conversion from this equation. So it would be Ra dot V is equals to minus Na0 dx upon dt, right? This is what we have calculated now, right? This is from the mole balance equation, right? I hope this much is clear, right? The value of dNA upon dt is from here. We have calculated from here. Just remember this, right? Now in this equation, just remember one thing, that reactants are decreasing and products are increasing, right? So number of moles for products will increase. For C and D, the number of moles will increase, whereas for A and B, the number of moles will decrease, right? So now we'll use this concept. Right? Now for say C, at any time T, how much it would be? Initially, say you have taken NCI, right, plus how much will increase? We'll write it, the increase would be equal to the conversion of A, right? So we'll write it in terms of A plus Na0X, right? This much have increased, right? So number of moles of C that has formed, right? Number of moles of, say, number of moles of C that has formed is equals to, sorry, we are doing it in terms of conversion. X is equals to, for conversion for C, right? Number of moles of C upon, we are calculating it in terms of A, right? So how much moles we have initially taken for a reactant A, right? So for NC at any time t would be Na0x. This much has Na0, this much moles of A is formed, right? That means this much moles of C has increased. Same is for D, right? Now for second order reaction, we know one thing. For second order reaction, the rate of reaction is right. For this second order reversible reaction, the rate would be right. This is how the rate of reaction would be given for the second order reaction. Now we will be using this equation. We will find the concentration of reactants and products and will substitute in this equation, right? So let's quickly do this. This is easy to do. We have done this in previous lectures also. Concentration is moles upon volume, right? Now if you remember, volume, we will be using V is equals to V0 plus nu 0 T. Nu 0 is molar flow rate, right? This we calculated in the previous lecture, right, where we have defined semi-batch reactor equation in terms of concentration, right? If you remember, when we did mass balance, overall mass balance, right, from overall mass balance we got this. This is your volume at any time t, right? Because when you are adding B, the volume is increasing, right? So volume at any time t is given by this equation, right? So for volume we would be using this, right? So for A, the number of moles would be, it would be Na0 1 minus x divided by V0 plus nu 0 T. This is your Ca, right? Similar, this is number of moles at any time t we have calculated here. Similarly, Cb would be number of moles of B at any time t, right? We have already got it from this equation, right? Nbi plus Fb0 dot T minus Na0 x divided by nu 0 T, right? Similarly, concentration of C, right? Concentration of C, these are the number of moles of C at any time t, right? Number of moles, we have plus sign here. Why? Because number of moles of C, which is product, is increasing, so we use plus sign here. But here we have used minus because number of moles of A, which is reactant, is decreasing, whereas those of product, which is C, is increasing, right? So it would be number of moles of C initially would be 0, so remaining would be Na0 x divided by V. V would be V0 plus nu 0 T. Similarly, Cd would be Na0 x V0 plus nu 0 T, molar flow rate, right? Now what we will do is, we will substitute Ca, Cb, Cc, Cd in this equation, right? And we'll rearrange everything, right? What you will get is equation as dx upon dt right, dx upon dt 1 minus x, right, 1 minus x plus NBI plus FB0 minus Na0x, right, minus Na0x square, right, Na0x square divided by K, right. You will get this V is common in all, right. So this is the equation of semi-batch reactor in terms of conversion X, right. This is simple. Let's just do it one more time. Initially the number of moles is Na0, you are adding number of moles of B, right. Since you are adding number of moles of B, remember the volume will change, right. So number of moles of A initially is this much, right. So since we have to calculate write down the equation in terms of conversion X, so we have to bring conversion in picture. Conversion is number of moles of A reacted, number of moles of A initially you have taken, right. It would be Na0x, this much moles of A has reacted, so remaining would be Na0 minus X, right. So at any time t, number of moles of A is this much. Similarly, number of moles of B, right, would be this much. Initially, let's say NBI is the initial number of moles which is present in the reactor, which we know is 0, right, plus number of moles added to the reactors, this, minus number of moles of B that has reacted, right, minus Na0x in terms of we have calculated number of moles of B reacted in terms of conversion X and in terms of reactant A, right, this, so minus Na0x, right. So NB would be, this is 0, you have got this. Now we'll do mole balance on A. Mole balance is in minus out, G plus A, you got this, right, this is what you will get. So dN upon dt, dNA upon dt is calculated from this equation as this, so right, so you will substitute it over here. Now we know that you have to remember this equation. Rate of reaction for second order reactions is this. Now you have to calculate the concentration of these reactants and products, and we know that concentration is moles per unit volume. Moles is, we have calculated moles at any time t using these equations, right, Na, right, Nb at any time t. Similarly for products it would be increasing. We have done this using stoichiometric tables that we used to build earlier, right, in previous lectures. You should remember, you can check my previous video lecture on stoichiometric table for batch systems, right, you will understand this. So from stoichiometric table we can directly take the concentration or the number of moles of C at any time t as NCI plus Na0x. Now all the moles we are calculating in terms of reactant A, right. So NCI plus Na0x, why plus, because number of moles of products are increasing, right. So you will substitute all these values here. So, and volume, remember this we have calculated in the previous lecture, V0 plus nu 0 T. So you will substitute value here, this is the equation that you will get, right. I hope this much is clear, right. Now we'll look at the second part of calculating the same, right, semi-batch reactor or the conversion at equilibrium, right. We'll be using the concept of chemical equilibrium now, right. Chemical equilibrium you have done in school, right. In school chemistry we have done chemical equilibrium. In chemical thermodynamics also you have chemical equilibrium, right. So now let's do that. For a reversible reaction in semi-batch reactor, right, conversion is when you get the maximum conversion for this reaction, right. When will you get the maximum conversion? At equilibrium, right? When equilibrium will attain, you have maximum products, right? And the reaction is at equilibrium. That means no reactants are converting into products, or the amount of reactants that are converting into products is equal to the amount of products that are converting back into reactants, right? So at equilibrium you have maximum conversion. We have to calculate that conversion. At equilibrium we have maximum conversion, right? And this maximum conversion is increasing, right? Just look at here, this maximum conversion is increasing because you are adding B to the reactor A. To the semi-batch reactor you are adding B. So as you keep increasing reactant, this reaction will move towards right, that is towards product side, right? Now for this reaction, we know that for this reaction at equilibrium we have concentration of products divided by concentration of reactants, right? Or product of concentration of products divided by product of concentration of reactants, right? So this is concentration at equilibrium of C, concentration of D at equilibrium, right? Concentration of A at equilibrium, concentration of B at equilibrium, right? Concentration is moles per liter, moles per unit volume, right? So NCE, number of moles of C at equilibrium, number of moles of D at equilibrium, number of moles of A at equilibrium, number of moles of B at equilibrium. These B will cancel, so Kc would be NCE divided by NAE dot NDE divided by NBE, right? So you have to calculate the number of moles, right, at conversion. You have to calculate the number of moles at equilibrium. Once you know that, you will solve this equation further, right? So from here we have already calculated, right? We have already calculated these as Na0xe, Na0. If you remember, the concentration of D was, concentration of C was NCI plus Na0x. This was the concentration at any time t. Since initially the concentration of C was 0, so concentration of C is now Na0xe, that is conversion at equilibrium. Same is for D. Right, now you have NAE, right? Number of moles at any time for A. If you remember, it was this 1 minus X, right? And for B, it would be, if you remember, NBI plus FB 0T, right, minus Na0X, right? Now if you calculate this, if you solve this, right, Na and this will cancel out, right, everything. This is your Na0. One Na0 will cancel out. If you solve this, you will get Na0 divided by NB0 K, right? Sorry, divided by, you have FB0 here. Na0 upon FB0 K. Then you have KCXE, right, minus XE square 1 minus XE. This is the equation at equilibrium. right? That means this is the equation for semi-batch reactor, right, at equilibrium, right? XC stands for conversion at equilibrium, right? I hope this is clear. This is simple. You just have to use this formula of chemical equilibrium that we do, right, that we used to do in chemistry. So this is Kc, concentration of products upon concentration of reactants, and concentration we know is number of moles upon volume, right? Number of moles at any time. This Nc, Nd, Na, Nve is number of moles at equilibrium. At equilibrium, we know number of moles is calculated using these formulas. We'll substitute, you reach out this equation, right? I hope this is okay. Thanks.